Hi everyone, so this week we'll be doing mole ratios and reaction stoichiometry. The purpose of this lab is to investigate the mole ratio between reactants and products in a chemical reaction and calculate the percent yield of that reaction. So a typical reaction, you have reactants and products, which you can see here. The reactants are A and B, and the products are C and D. The lowercase letters here correspond to the moles of each substance. So you'll see in a chemical reaction that you'll have a certain number of moles of reactants, and you will produce a certain number of moles of each of the products as well. So our goal is to figure out the ratio between the reactants and the products of our chemical reactions in this lab. And so, for example, if we want to see the ratio between C and A, we will divide the lowercase c by the lowercase a, which corresponds to the moles of the product over the moles of the reactant that we want to look at. So we'll be doing two reactions in this particular lab. The first is a reaction between sodium bicarbonate and hydrochloric acid, which will produce sodium chloride, carbon dioxide, and water. So if you'll notice this equation here, the first substance is your sodium bicarbonate, and then you will add hydrochloric acid and get salt and carbon dioxide gas and water. Our second reaction is with sodium carbonate and hydrochloric acid, and we should produce the same sodium chloride, carbon dioxide, and water. Notice the names of these, sodium bicarbonate and sodium carbonate, are very similar, so be sure to pay attention as you're watching the video and doing your report sheets, that you know which one you're talking about when you're doing calculations and things like that. So our procedure, we'll start by adding 0.3 grams of sodium bicarbonate into an evaporating dish, and then we'll make sure to record the mass of the whole setup with the sodium bicarbonate. Then we will add hydrochloric acid drop by drop until we see that the reaction is complete. So during this particular part, carbon dioxide will start to form as a gas and will start bubbling out of the solution. So once we see that bubbling stop, we know that that part of the reaction is complete. And so all that should be left in our evaporating dish is salt and water. So our next step is to use the Bunsen burner, as you see set up here on the right. And we're going to dry the salt water basically until it is just dry salt. Then we will record the final mass of the dish, watch glass, and the salt after heating, after that has cooled to room temperature. So we will do this process, and then we will repeat this with the sodium carbonate. It's the exact same procedure. So just some notes about Bunsen burner safety for your knowledge. It's always important to check the tubing between the burner and the gas valve for any cracks or imperfections, because you don't want any gas escaping, which could potentially catch on fire in your hood and in the air, so that wouldn't be good. And to secure all your loose clothing, long hair, things like that, that you don't want catching on fire, and to always pay attention when you have it lit. Don't leave it unattended. And then to light the burner, you'll see in the video how I do it, but you'll first close it, which means turning the barrel all the way closed. Then you turn on the gas from the valve, and you can light a match, or there are strikers if you've seen those before. I'll be using matches, and you will see the flame spark and will light. And you'll notice in the flame, in the picture here, there's a middle cone that's smaller and a very deep blue color. That is actually the hottest point of the flame. So in this case, we don't want too strong of a flame, so we're going to aim to get that top part of the flame interacting with the evaporating dish, because we don't want it to be too hot, we don't want it to burn too quickly. So that top flame, the larger top blue flame that you'll see, is the one that we're going to use for our experiment. So the calculations for this lab, the first part of it is determining the mole ratios in your reaction. So if this is the sodium bicarbonate reaction, and you can see from the stoichiometry, which is just the notating the moles in front of each substance in the reaction, you can see that the ratio between the NaCl, the salt, and the sodium bicarbonate is a 1-to-1. So the mole annotation in front of these says 1 for each of them, so that's a 1-to-1 ratio. So we're going to calculate our specific experiment to see if that is true, if we can get that 1-to-1 ratio. So how do we do this? First, you're going to convert your starting mass of sodium bicarbonate to moles. And that's pretty simple. You just divide it by the molecular weight of sodium bicarbonate, which this is just an example calculation. But from the mass that we started with, we can find the moles. Then we will convert the product mass to moles. So same thing, however much salt we end up with at the end, we'll divide that mass by the molecular weight, and we can figure out how many moles we have. Very important note, make sure you subtract the evaporating dish and watch glass mass, otherwise your numbers will be really crazy. So make sure that's always subtracted when you're finding the mass of things. Then we're going to divide the moles of salt by the moles of sodium bicarbonate to get that whole number ratio. So in this example, I divided the moles of each and I got around 0.94, which is pretty close to 1. So that's what you're aiming for, is as close to 1 as possible. That means that the reaction's completed and everything went pretty well. Just a note about sodium carbonate, the molar ratio here is not 1-to-1. If you'll look in the reaction, there are actually 2 moles of sodium chloride per 1 mole of sodium carbonate. So the stoichiometry here is a 1-to-2. So when you divide the moles of salt by the moles of sodium carbonate, you should get a value around 2, not 1 like you did with the sodium bicarbonate. So pay attention to that as well when you are calculating your mole ratios. The other half of the calculations will be a percent yield. So I'm using the sodium bicarbonate reaction as an example here. So the percent yield is the experimental yield divided by the theoretical yield, and then you'll multiply that times 100 to get a percentage. So first step in this is to calculate the moles of your reactant, which in this case is sodium bicarbonate. So same process as before, you'll take the mass of your starting material, divide it by the molecular weight, and get the moles. Then you can convert those moles to the moles of your product using that molar ratio. So remember, when you're converting units or measurements or things like that, you're putting what you have on the top and then dividing by that value. So here we start with the moles of sodium bicarbonate, and we're going to put that on the bottom of our conversion factor because we want to end with the moles of sodium chloride. So you divide by the molar ratio, which Conveniently, for sodium bicarbonate is 1:1, but remember, for sodium carbonate, that will be a 2 divided by 1 for the conversion factor. So definitely pay attention to that in your calculations for number 2. The next step would be to convert the moles of your product, which you just calculated, to the mass of product. And to do that, you will multiply by the molar mass of salt. So this step gives you your theoretical yield. So your theoretical yield is totally calculation based. It's based on what you see here. It's based on what you started with, and your theoretical yield is saying, okay, this is how much sodium chloride I expect to produce in my reaction. So that's what theoretical yield means. And then your experimental yield you have already found, which is how much sodium chloride you actually weighed out after you heated everything up. So you'll divide your experimental by your theoretical. And for my example, in the previous slides, my mass of sodium chloride was 0.20 grams, and I just found the theoretical yield was 0.21 grams. So I'm going to divide those and multiply times 100, and that gives me a 95% yield.